Alright, so I've gotten a couple of requests this morning to answer a few questions, so we'll go ahead and get that out of the way first. First is the study guide mentions converting between KQ and Gibbs free energy. Could you work through an example of that? And this is something that is on the packets, so I'll bring up the packet problems for you. So simple ones here, we've got a KQ equals 1.30 times 10 to the negative 33, and we're asked to find delta G naught, the reference free energy. We're going to find, when I talk about how we're going to solve this, you're going to find two things. First of all, the reaction doesn't really matter. We're more focusing on this KQ number. The second is that the second type where you find KQ from delta G naught versus delta G naught from KQ. They're really the same problems, they're just being solved in reverse orders. So to solve these types of problems, we've got two relationships, so the same relationship just rearranged. In this case, KQ equals E to the minus delta G naught over RT, or delta G naught equals minus RT ln KQ. Now, R here is going to be your ideal gas constant, 0.008314. Temperature, the problems giving in the packets are 25 degrees C, so 298 Kelvin. So really with these types of problems, it's just plug and chug. In terms of what's a reasonable answer for delta G naught, plus or minus 25 to 150 kilojoules per mole. Now again, this is kind of an arbitrary right answer. There are definitely delta G's less than 25. There's definitely delta G's greater than 150. Most of life operates in this 25 to 150 regime. In terms of the KQ itself, there is no reasonable answer for that. Definitely not 1, because then delta G would have to be 0. But really, in terms of what values KQ can take on, it can be super teeny tiny, like 10 to the negative 33, or it can be enormous, 10 to the million. Typically for the problems we work with, the KQs are very small. But that's because we're working with basically reactions that have a very unfavorable free energy change. So, second question I've been asked. Entropy without tables and enthalpy without tables section of the study guide. Could you please show how to set up and work an example of one of them? So, I'll bring up we'll do the Gibbs without tables. These are solved the same way. So we'll work with this top problem. Where's my eraser? Here you are. So here we got ethylene, C2H4, plus 3O2 goes to 2CO2 plus 2H2O. We have a delta H here of minus 1,314. For the second one, we've got 2H2 plus O2 goes to 2H2O with the delta H of minus 457.2. Third reaction, carbon plus oxygen goes to CO2, the delta H of minus 394.4. I'm sorry, these are delta G's, not delta H's. Force habit. And the last reaction, 2 carbon plus 2H2 goes to C2H4, and this is the reaction we're trying to solve. So there are two ways of approaching these types of problems. The way I'm going to recommend you learn how to do is Hess's law. So for Hess's law, what you're going to do, write out the Hess's law expression for each reaction. So in this case, it's products minus reactions, so the delta G equals 2 times the Gibbs of CO2 plus 2 times the Gibbs of H2O minus the reactants, the Gibbs of C2H4 plus 3 times the Gibbs of O2. And this is going to equal minus 1314. For this, delta G equals twice the Gibbs of H2O minus twice the Gibbs of H2 plus the Gibbs of O2. This is minus 457.2. Here, delta G is the Gibbs of CO2 minus the Gibbs of carbon plus the Gibbs of O2. This is minus 394.4. And the last one, we want to know the Gibbs of the reaction, so the delta G is the G of C2H4 minus twice the Gibbs of carbon plus twice the Gibbs of H2. Now, Again, this is applicable for both the Gibbs and the enthalpy. So the early problems in those packets were to ask about the H. It's instead of G's, you got H's, but it's the same approach. So first step, write out all the G's, write out all the Hess's laws expressions. The next is cancel out all zero terms. So if you have a pure element, carbon, carbon's going to be the only pure element in here. If you have something like lithium, sodium, magnesium, phosphorus, something that doesn't have a subscript, it's just one element, that is zero. The exception there are diatomic gases. Diatomic gases themselves have a zero Gibbs and enthalpy formations. So see, O2, N2, I2, F2, Cl2, Br2, and H2, all their enthalpies are zero, all their Gibbs are zero. But the monatomic version, so if you had H or you had O3, those are not zero. So basically it has to be whatever these elements would be at room temperature in 1 atmosphere. So up here, CO2 is definitely not zero, it's 2 elements bound together. H2O is definitely not zero, it's got 2 elements bound together. C2H4, 2 elements bound together, definitely not zero. O2 is a diatomic gas, so this ends up going to zero. Here, H2 goes to zero, O2 goes to zero. Here, carbon goes to zero, O2 goes to zero. Down here, carbon and hydrogen both go to zero. So we're just going to erase those off. So from this, I get twice the Gibbs of H2O is minus 457.2, or the Gibbs of formation of H2O is minus 228.6 kilojoules per mole. For this, I get the Gibbs of CO2 is minus 394.4. Up here, I don't know the C2H4, but I do know the H2O from here, and I also know the CO2. So I'm just going to rearrange this. And for the 2H2O, I have minus 457.2. For the CO2, it's twice this number, so 8 minus 788.8 plus negative 457.2 plus 1,314. Whatever number we get up here, we're just going to stick it in down here and use that number to figure out the delta G of the unknown reaction. Next question, molar mass and molar solubility problems is example shown in the study packets. So let me bring back up the desktop. So the thing to note with these types of problems, if you go back to the previous examples, concentrations from KSP, you see there's aluminum phosphate, barium bromate, beryllium hydroxide, and then it's asking you the exact same compounds, barium bromate, beryllium hydroxide. The reason being is that it breaks the concept into 2 steps. So in order to figure out molar solubility and mass solubility, we have to do the previous example. So we have to figure out the concentrations of the different components. So let's start with aluminum phosphate, AlPO4. So we have, I guess I can switch to blue. For any type of equilibrium problem, you need 3 things. We need KQ equals Q, and in this case we're given that the KSP equals minus 980 equals 984 times 10 to the negative 21. So we need KQ equals Q. So KSP here equals Q, and our expression for Q is the concentration of aluminum times the concentration of phosphate. We're also going to need our IC table. Now again, I can leave off any solids or liquids because they are not going to be involved in my expression for Q. I've got I, C, E, E. I've got aluminum. And I've got phosphate. I'm not given any starting concentrations, so I'm going to assume they're 0. The change is whatever number is in front of the compound times the extended reaction X. So there's a 1 in front of this aluminum, so I have plus X. Plus X. These are positive because they are products. If there was a reactant here, the change would be negative. This E row is the I plus C, so we get 0 plus x, 0 plus x, and E here is the numerical value. So originally what it asked for earlier in the packet is what's the concentration of phosphate and aluminum. So since we're looking for these squares, we stick in and we get that x squared equals KSP, so x equals the square root of KSP. Now, to figure out the molar solubility and the mass solubility, it's actually pretty straightforward. The molar solubility is just the extended reaction X. And the way that works out, reason that works out, is that if we were to include the aluminum phosphate in here, the concentration doesn't matter because it doesn't show up, but what we would find is that the change here is minus X. So that's how many moles per liter are dissolving in the aluminum phosphate, and that's what a molar solubility is. It describes how many moles of the solid dissolve in per liter of solution. Now, to figure out the mass solubility, all we do is take the extended reaction, multiply it by the molecular weight of the compound. So we would figure out how much aluminum phosphate weighs and just multiply it by its weight. So for all problems involving KSP, and KSP problems are going to be where you find the mass solubility and the molar solubility. The molar solubility is just the extended reaction you solve when you solve out this IC table, and the mass solubility is just that extended reaction times the molecular weight. And I think that's all. Yep, that looks like all the questions. So, are there any questions for me today? So the reason why the reactant doesn't show up is that it doesn't appear in our expression for Q. We could create a column that has it, but at the end of the day, it's irrelevant. So it's kind of like doing work for the sake of doing work. If you have any solid in any liquid, they don't appear in the expression for Q, so generally they're just kind of left out of the IC table because the information is irrelevant. Now, if the aluminum phosphate was like dissolved in water, like it was AlPO4 AQ, then it would appear in the IC table and we would worry about it. The other thing is that for a solid or a liquid, the concentration is kind of a meaningless number. It's going to be astronomically high. So I think water, pure water, is 55.6 molar. So you can get a concentration, but it's the concentration of the solid in the solid phase, or it's the concentration of the liquid in the liquid phase. So physically, what happens? Physically, why we use concentrations as Q's is that it describes basically driving force, and that driving force comes from concentration. You can't change this concentration of a solid or a liquid very easily. I mean, you would have to go to like super high pressures to make that happen. So the concentrations for the solids and liquids do actually appear in the expression for Q, but they're divided by their activities, and their activities equal their concentrations. So you need, if you're really interested in that, we can talk about where Q actually comes from. But generally speaking, the reason why we leave the solids and liquids out is because they cancel out in Q. They disappear. You're welcome, Michaela.
concentrations from KQ. So the question is problem 3 and 4 from the homework for concentrations from KQ. So I'll share the desktop really quick. So the first one is if we have H plus solution and we've got sulfurous acid, H2SO3 dissolving. And we're giving the starting concentration of H2SO3 is 0.223 molar. And the starting concentration of HSO3 as 0.0190 molar. And we're being asked to find the concentration of H+. And we're given that the Ka is 0.0154. 0.0154. So to solve this type of problem, we get the Ka equals Q. Q is the concentration of H plus times the concentration of HSO3 minus 1 all over the concentration of H2SO3, and these are specified at the equilibrium concentrations. So if we build our IC table, we have H2SO3, H plus, and HSO3 minus 1, ICEE. And we're being asked to find the constant of H plus, so what we need is this square here. We're given initial concentrations of 0.223 molar. We're not given H plus, so we treat it as 0, 0.0190, minus X, and plus X. So we give us 0.223 plus X, and 0.0, sorry, not plus X, minus X, plus X. So since we're solving for this row, odds are we're going to need the row above it. So we stick this in, we get X plus 0.0190 all over 0.223 minus X. Now, if we rearrange this, I'm going to keep Ka as Ka just to make the numbers a little bit easier to see. If we distribute over, we get X squared plus 0.0190X equals Ka times 0.223 minus X times Ka. We rearrange, we get X squared plus 0.0190 plus Ka(x) minus Ka times 0.223. And here you would move to the quadratic equation. I'll build an Excel sheet really quick. So let me share the Excel sheet with you now. Okay, desktop. So this is the starting concentration of the H2SO3. This is the starting concentration of the HSO3 minus 1. So from the equation I had written up on the board, the A term is what's multiplied by X squared, that's 1. The B term is going to be the 0.0190 plus the Ka. And our C term is going to be the Ka, negative Ka, times 0.223. Yes, that is a mistake right there. Nope. So I've got two roots here. 0.0439 and negative 0.0783. The reason I know this root is wrong is not because it's negative, but I know that the concentration of H plus equals X, and so if X is negative, I have a negative concentration. So if I look it up, I get 0.0438 as the answer. For the one beneath it, H plus concentration, if we have HN3, and, oh, that's an even easier problem. Give me a minute just to transcribe that one. So we've got HN3 going back and forth to H plus, N3 minus 1, with a Ka here of 1.9 times 10 to the negative 5. And the concentration of HN3 is 0.5 molar, everything else is 0. So again, so my my expression for Q, it's H plus times azide divided by HN3. Need my IC table. So I have HN3, H plus, N3 minus 1, initial change, end. Initial for HN3 is 0.5. H plus and N3 minus are 0. We're not given them. Seems like an oddly easy problem. Here's what it is. Change is minus X, X, and X. And again, it's not, this isn't always true. It's going to be multiplied whatever's in front of the reaction. In this case, this all happen to be 1. So I get 0.5 minus X, X, and X. And I'm being asked to solve for the H plus concentration again. So it's going to be this square that I'm getting at. If I plug it back into my equilibrium expression, I get X times X, 0.5 minus X, all this equaling Ka. If I rearrange, I get X squared equals Ka times 0.5 minus X times Ka. So X squared plus Kax minus 0.5 Ka equals 0. If I use the quadratic equation, I'm just going to finish this up. E to the negative 5. Again, I get two roots, 0.003073 and minus 0.00309. The negative root is not the correct root. This is not because it's negative. It's because I know the concentration of H plus equals the extended reaction. So if the extended reaction is negative, I get negative concentration. So I would recommend using Excel for the homework. The hard limitation with these types of problems is that most KAs are teeny tiny. Now for your test that you're taking this week and next week, I intentionally used large KAs because hand calculators, particularly the TI-34s, I'm not so sure about the TI-84s, generally can't handle KAs this small. So you start seeing issues with rounding. Like it doesn't carry enough decimal points to account for the accuracy. But again, your exam, I intentionally saved the examples for your exam because they have large KAs and they're less likely to create issues with calculators. Also in your exam, this is like 80 to 90% of the credit. So if you've got it set up and you end up with a wrong answer, you're more likely going to get like 80 to 90% of the credit just because you clearly set it up, just for whatever reason you didn't get the right answer. And Michaela's pointed out, yeah, Excel is kind of hard, and typically it's kind of a disservice that you're not doing the lab or a seated lab. In the seated lab, I don't allow you to use calculators. You're required to use Excel for all the problems. So at this point in the course, you would actually be pretty comfortable with programming in Excel, or at least kind of like know sort of what you're doing. Excel is a super awesome program. It is one of the most valuable skills you will learn in this course, which, saying this somebody who teaches chemistry, that's an honest statement for you right there. Excel is incredible to use. As you probably just saw with the Excel sheet I had, the only thing I had to do was change the numbers and it automatically updated the roots. So if you build an Excel sheet to solve these types of problems, At the end of the day, you just have to change the numbers and it will automatically update your answers. In fact, Excel was used to generate all your homeworks because I could give it whatever KAs I wanted. It also has a random number generator, which is really nice. But yeah, the homework's going to be a little bit more problematic for you for finding the H pluses, simply because, yeah, a lot of calculators have trouble carrying like KAs that are that small, but your exam is set up to have large KAs to kind of get around that issue. Big thing though is just understanding how to set the problems and understand the concept. Now, just in case you're not familiar with Excel, one thing to keep in mind with Excel, each cell, when you enter a formula, you need to set up the formula that the value you're spitting out is the Y, and what you're programming into the cell is the formula in the cell. When I use this X vector, you can actually program it to just basically read out of cells. So you can put in numbers and use it like a calculator, but it's a lot more powerful if you just solve with variables and then make the variables cells within your Excel sheet and just reference those variables. No, I can show you how I set it up. Like, we can do it right now, actually. Okay, I'm assuming my connection came back. All right, so for setting up these Excel sheets, with these problems, you probably picked up a pattern. There's a Ka, there's initial concentration, there's a final concentration, and if we just set up a general case on the board, oops.
So I just have HA going back and forth to H plus
and A minus. I would definitely say the steady packets are the most useful for this particular exam because they have the huge chunk of thermo problems in the back. But that's really, there's not much else. I mean, this test is hard because there's just hard concepts on it. It's not a long test. It's only 13 questions. 10 of those are multiple choice. The rest are very much open, free response and show your work kind of problems. That said, the 3 problems do have multiple parts to them. So I think there's 3 parts to each one. But again, if you can do the packets and the homework's just there to kind of give you practice with the ones that have numerical values, you're going to be just fine for this exam. Anyway, so if we have a problem with the general form, some acid dissociating, and it has some Ka, that's our expression for Q, our IC table. HA, H plus, A minus. If we just have some starting concentrations, concentration at HA, 0, A minus, the change is minus X, X, and X. So we get HA minus X, X, and A minus plus X. I can plug in, I get X, times a minus minus x all over j minus x. When I rearrange and solve this for x squared, I get x squared plus ka plus a minus times x minus ka times ha equals 0. These are just variables now. So I've got a, b, and c for my quadratic equation. So that's the way I've set up my Excel sheet. So I've got HA, A minus. A here is whatever's on the x squared. In this case, it ends up being 1. B in this case is just Ka plus the conjugate, or the A minus. And C is just minus Ka times HA. Nope, don't want you to do a formula. And so that's what I've entered in here. It's minus Ka times the starting concentration of the acid. And B here is the A minus plus the Ka. The quadratic equation, this is the opposite of B, plus the square root of B squared minus 4 times A times C divided by 2 times A. And then I just took the formula, copy and paste again, and switched the positive to a minus. And you could build your full IC table. Oops. And we're going to have our X here. E rho is I plus E. And this would work it out for every case. So if we change A minus to like 0.25, it would automatically update what the root is and would automatically update all these values for us. Now the one thing Excel cannot handle is symbolic logic. There is a way to teach it how to do that, but in general it's not worth it. So the legwork falls on you to set up the cells to be functions. But once you've got, if you know you're going to be doing the same calculation over and over again, it's incredibly helpful because you just keep changing the numbers and it will automatically change the values. But particularly with labs, like a lot of your labs are, and you don't see it on the website. Traditionally what I do is I provide students with Excel sheets for the website. They're just whatever worksheets we use without any formulas in them. If students have the option of downloading the Excel sheet and putting the formulas in there while they're doing the lab, so this way they can do live updates of the calculations. I've had a few students that were precocious enough to actually like program the Excel sheets in advance. And when they showed up to the lab, all they had to do was put the numbers in. And once they got the numbers in, it automatically did the calculation. Yeah, you're very welcome. Like, Excel is an incredibly valuable skill. Like, this is a good time to start learning it. Because one major advantage your Excel sheet's going to have over a calculator, beyond precision, you can save it and open it up months later. So if you ever come back to the same problem, you can just take it up and open it again. This isn't going to be true with a calculator. A calculator only stores like the last 50 operations. So these will be good whenever you need to come back to them. As faculty, we've talked about asking for a creating a 1 credit hour course that teaches students basic Excel, Word, and PowerPoint skills. We'll probably never get it through, but this is something that, particularly as chemistry faculty, I was fortunate. I took an undergraduate chemistry course where the guy just taught Excel. So I would say half of what we covered was how to use Excel. The course was amazing because calculations got super easy. But students aren't always fortunate enough to have a course where they're required to use Excel. So it would be nice if we actually required like a 1 credit hour course that said, okay, here's how you set up an Excel sheet, Here's how you do formatting in Word. Here's how you do formatting in PowerPoint, and just kind of get you all the basics. Because you're in college now. Like, you should be using more advanced programs. I can't tell you the last time I actually owned a calculator. Most of the calculators I work with, I swipe from the lab. All right, other questions? All right, give you all about another 5 minutes, and if no one's got any questions, we'll head out for today. The problem CaCl2 to a molar. It's a pretty big number, so I'm guessing that's delta G. So the question's been asked about one of the problems on the homework, and the problem is this one here. Calcium chloride 2 molar, assume 2 molar, then what's delta G at 2 molar? So that's definitely correct. That would be 2 to the 5th power, because there's a cube there, a second there, so I agree with the Q. So let's go from there. So we've got 1 delta G equals delta G naught plus RT ln of Q. So delta G naught in this case is 164. R is 0.008314. Temperature, you're at 273 or 75 degrees C. So that's 348 Kelvin, ln of 32. So let's see what that ends up being. So I get 174. It looks like 174 here, so I'd agree with the key on this one. So as far as I can tell, there's nothing wrong with the key, because your Q here, concentration of calcium cubed concentration of phosphate squared, so you get 2 molar cubed times 2 molar squared. So that's 2 to the 5th power, which should be 32. 2, 4, 8, 16, 32. So yeah, as far as I can tell, there's nothing wrong with the key. Okay. Yeah, you're welcome. Every now and then, some of these are very old problems that I programmed, so every now and then one will kind of slip through, so it's good to catch them and see if there's any mistakes. There's also sometimes what I would consider a legacy issue, like when it was originally done, there was a mistake in how it was worded, that wording's been corrected, but you still kind of see the answer buried in there from when that mistake was in there. So it's just good to catch it. Particularly if I introduce a new homework problem, it's always good to catch it and see like if there's something wrong with the problem itself. So we'll just go ahead and cut it off for today. Thanks for all of y'all who show up. Again, keep in mind your exam's open until Tuesday, so you have the whole weekend to work on it. Typically don't look at exams on the weekends. I may try to, but you'll definitely get feedback on your exam within one business day. Again, remember that if you don't see a 1 out of 1 for your work, I haven't looked over your exam yet, so I'm going to have to give you time. Particularly with this exam, I'm going to need to look through your work. Again, any other questions you have, please feel free to email me, send me a chat, and I will see you all next week. Good luck on your exams.